Hi. So, what is the difference between solids, liquids, and gases? See, for instance, I will take on solid. Let this be a common thing. So, why we have to go into something extraordinary things, right? Okay. So this is a solid. So, it have a particular shape. So it is having half, cylindrical protruded with some pin, right? So it is definitely having a shape, and of course it is having a particular mass also, definitive mass as well as a definitive shape. So if I weigh this on a weighing balance, it will somewhere around, it will cost around maybe this will be around some maybe 200 gram or maybe 300 gram, so maximum. Okay, so that is the solid. Solids are always having a particular shape. Let it be a key. So this is also having a shape, right? Shape as well as it is having a size. Shape as well as having definitive mass. Now, on the other hand, if you take liquid, so let's this is again a reagent bottle. So it's measuring cylinder. So you see that if I pour this some water into this measuring cylinder, what will happen? So it is flowing, right? It's flowing. So it is obviously see, now it was previously it was occupying the shape of this long cylinder. Okay. Yeah, now it has occupied the shape of this particular measuring cylinder. Now when I pour that into this particular beaker, reagent bottle, it has occupied the shape of this reagent bottle, right? So this is how any liquid is. Liquids always, it does not have a shape, but of course it has some volume. If you see that, you can see how much is the volume. It is almost occupying 100 100 ml. So it occupies a particular volume, but it does not have a shape. That is actually the case of liquids. Liquids are not having a particular shape, but it have a volume. It definitely have volume, definitely have some mass. Okay. Solids, it has definite shape, definite volume, and certainly it has a definite mass also. On the other hand, if you are going to see the gases, see, I am trying to save some amount of gases in my mouth. Now, so those gases, it went out. So whatever the gas particles inside my mouth, it was previously how much it was occupying only inside my mouth. So how much is the volume of my mouth? It was occupying there. Now, when I blown out, those same gases, it start to occupy different bigger volume. So the gases does not have a volume, does not have a it doesn't occupy a particular volume, and it does not have a correct it has mass. It does not have a volume, does not have a shape. It does not have a shape, does not have a volume. Okay, it occupies whatever the volume it is, it occupies whatever the shape it is. If you are filling some amount of gases into this cylinder, it will occupy the shape shape of the cylinder. On the other hand, if I blown out, it will occupy everywhere around, everywhere in this atmosphere. Okay. See, actually, for a demonstration, I took some amount of gases. See the closer approach, you can see, and I am trying to keep it on this is nothing but a induction coil. Okay, this is nothing but an induction coil. So I increased the temperature. So what will happen actually when the ice, it remains as ice only at 0 degrees Celsius. See, ice is, as you are very familiar, ice is nothing but the solid form of water, right? I don't need to tell you anything. So I just started heating. Let's see what will happen. Actually, once you heat the ice, it goes into melting. Okay, it goes into melting, and it is after some time, when the temperature it increases, actually the ice you can see actually in the bottom, previously it was fully ice. Now you can see it is started to melt. Okay, yeah, within no time, maybe maximum just 2-3 minutes, it will go melting. Okay, so now in the next step, which you can see now, okay, which you can see actually, just observe it properly, see the fumes it is coming. So again, once you start it, actually this ice, when you start it again, so it will try to go as a vapor. Okay, actually, so that process from liquid to vapor, here what is happening, liquid to vapor, that is nothing but vaporization. So the first step in which the solid ice it is converting into, see, solid ice now it is almost very much converted. Solid ice it is converting into liquid water, it is melting, and the liquid water it is converting into vapor, it is called vaporization. Okay, and of course there are reverse processes which I will explain now. We all know that actually this water it evaporizes at 100 degrees Celsius. Right, actually water it evaporates at 100 degrees Celsius. It melts at 0 degrees Celsius. Okay. So now let's see about other things actually, like oxygen. See, oxygen we all know it is a gas. So obviously at 0 degrees Celsius, or like our room temperature, actually our room temperature oxygen will be existing as a gas. Obviously, even in 0 degrees Celsius or even in -5 degrees Celsius, even when you go to these places like Siachen or maybe Mount Everest or Mount Alps, so there also oxygen will be there, right? Actually, that means that oxygen it doesn't go into liquid state. It doesn't go into liquid state even at a very, very, very low temperature, which is on the earth. Okay, so the melting point of oxygen is actually very less. Actually, oxygen it is -219 degrees Celsius. See, in the case of gases, okay, there are two conditions are there in order to liquefy this. Okay, so one is you need to apply high pressure. Next is you need to lower the temperature as much as you can. Okay, so these two things are there actually. So when you decrease the temperature as much as you can, and when you increase more pressure, obviously there is when you decrease the temperature, what will happen? See, when these particles it will be moving, right? Actually, these gas particles, oxygen, it is keep on moving. So the movement of the particles, actually the vibrational energy or translational energy or rotational energy, this energy it reduces. So obviously when it is moving like this, okay, when the temperature is slowing, it will its motion will almost ceases, and so it will try to remain in less motion state. So proportionally, when you decrease the temperature and increase the pressure, these particles it will come closer and closer. Okay, so this is the case, and it will try to occupy a lesser volume. Okay. It will try to occupy a lesser volume. So this is the case of oxygen. Not only oxygen, majority of the gases. Okay, and its boiling point -183 degrees Celsius. And ethanol, similarly ethanol, once you pour some ethanol, probably those who are going to hospitals, they will be wiping our skin with the ethanol. Okay, so this ethanol, when you wipe it, you will feel coolness, because even in room temperature it evaporates. Ethanol, its melting point is minus -15 degrees Celsius. and boiling point is, you can, it is 78 degrees Celsius. Similarly, even just on the, just if you boil itself, even before reaching 100 degrees Celsius, ethanol would be boiling. Okay, and now for extra next one, sodium. Sodium is a very soft metal. It's a metal actually, but it is a soft metal. You can just with a knife, even you can cut it. Just with a knife, you can cut it. Okay, so that is the case of sodium. So sodium, its melting point, it would be, it is actually 98 degrees Celsius. Even before reaching 100 degrees Celsius, it will melt. Boiling point, it is 890 degrees Celsius, which is slightly very lower than other metals. Okay, and for sulfur by I put S8 actually, it is it's a 8-member one sulfur molecule, it have 8 sulfur atoms. Okay, so actually sulfur will exist in this way. This is the sulfur molecule. Okay, this we call it as a bucket ring structure, or like it's a crown structure. Okay. Okay, so and now the common thing, iron. Iron, its melting point is around 1540 degrees Celsius, but for its boiling point it is 2990 degrees Celsius. Okay, it's slightly higher. And when you take diamond actually, its melting point is it's around 3550 degrees Celsius, but the boiling point, see, even a diamond is one of the hardest substance which you are very familiar, right? Actually, a diamond doesn't it doesn't break, or even when you apply the forces, okay, nothing will happen to that. Okay, that is the case with the diamond. Okay, so yeah, so this is the case of diamond, and its boiling point is a very high. It is actually 4882 degrees Celsius. Actually, this higher boiling point, this high temperature, like 1000 degrees Celsius or above 1000 degrees Celsius under. Okay, we cannot normally get it with normal instruments. We often go into furnace, like molten furnace. Those type of things, actually electric furnaces. So those electric furnaces under it heats the it attain this very huge temperature, so that this diamond, it would be melting. Okay. Okay. Now we will go into see some. We will draw a temperature curve. In fact, instead of I am narrating so many things, instead of I am telling so many things, sometimes a picture speak multiple 1,000 times. There is a word, right? A picture speak 1,000 times than a word or like a sentence, right? See, usually for whichever the substance it is, we used to draw some heating curve. Heating curve is how much temperature it is. See, this is, I am going to draw the heating curve of water. Okay, so this is actually 0 degrees Celsius. So this is actually melting. So when the temperature rises above 0 degrees Celsius, okay, this, the ice, it just start to boil. Like when we keep on going above 0 degrees Celsius, ice start to this is actually liquid state. This start to evaporate. So slowly. Actually, even in our 30 degrees Celsius, 40 degrees Celsius, or 25 degrees Celsius, normal temperature in many of the countries is 25 degrees Celsius, right? So even in 25 degrees Celsius, if we pour some water outside, we don't see it after some time because it undergoes evaporation even at 25 degrees Celsius. So some amount of evaporation will happen even in 30, even in 40 degrees Celsius. Okay, some evaporation, some evaporation happen. So this is 100 degrees Celsius. Once it reaches 100 degrees Celsius, it will start to boil. Okay, it will start to boil. And above 100 degrees Celsius, water, it will try to remain as a vapor. Okay, so that means actually beyond 100 degrees Celsius, no water, it will try to remain as a liquid. Okay, unless you apply some high pressure. But in normal cases, if once it reaches above 100 degrees Celsius, nothing will remain as a vapor. Nothing will remain as a liquid. The water, it will go as a vapor. So this is actually okay. You can say 120 degrees Celsius or anything above 100 degrees Celsius. Actually, this form of representation is called heating curve. Okay, so that means actually we will draw I versus temperature. Time versus temperature graph, if you are drawing, that is actually we call it as a heating curve. That means how much time we take for melting, how much time we take for boiling, how much time we take for evaporation. Actually in this range, actually 0 to 100 degrees Celsius. Okay, the water, it will try to remain as a liquid. Below 0 degrees Celsius, that means below 0 degrees Celsius, water, it will try to remain as a solid. Above 100 degrees Celsius, water, it will remain as a gas. Okay, so this is the case. This is nothing but a heating curve. So it represents actually how easily and how nicely this the evaporation, I mean, like from for a particular stuff, let it be water, or it could be some metal or diamond or inorganic metal, whatever it may be. So in which temperature it is melting, and which temperature it is remain as a liquid, which temperature it will go as a vapor, it will go in the gaseous state. We will get it beautifully when we draw a heating curve. Okay.